So today we have an exciting physics hero called Isaac Newton. Has anybody ever heard of him before? Good. He should be a familiar name because Newton was a major nerd. He was actually smart enough that he could have hung out with me. So it was pretty good. He lived about 350 years ago, but what's impressive is if you think about how much science has changed over the last 350 years, it's like incredible in all the fields of science except in physics. It's not that we haven't gone places in physics, but the basics of physics haven't changed at all since Newton was around. Most of what we now call physics he came up with. In fact, he figured out so many things that other scientists of his day complained, don't even go into physics, Newton's got it all figured out. There's nothing left to be discovered. So that's kind of cool. When his math got complicated, he invented his own simplified version, which we call calculus. If you've taken calculus, you say, well, that's kind of complicated, but if you see what it replaced, that was much, much worse. His teacher was a guy named Galileo Galilei, which I have no idea what his mother was thinking. But Galileo took the telescope from a toy and turned it into an actual optical instrument that you could use, and from that he saw some things that changed the way that we look at the world. And he also came up with the 5 formulas that we dealt with last week. And so his teacher dealt with those formulas. So Newton was trained in that sort of thing. But what we're going to learn in Unit 11, he came up with the formulas that we're going to learn about optics. He came up with the concept of universal gravitation that we'll cover in Unit 6. But what's cool about Newton was Newton didn't think he was all that. One of his famous quotes is, if I have seen farther than most, it's because I've stood on the shoulders of giants. He saw himself as a little person, and all the people that came before him were the giants, and he just thought, well, I could see because of all the work that they did. I just happened to come along at the right time. He didn't see himself as all that, which is pretty cool. Most importantly for this unit, Newton came up with 3 EWSHs. So other people have come up with these ideas and part of these ideas, but what happened was back in those days people thought motion was incredibly complicated and too hard to really understand. And he said, no, really motion can be divided into 3 simple rules, and if you look at these simple rules, you got it made. Some people call these Newton's laws of motion, but we don't like the word laws. That's bad. We don't like laws because when you hear the word law, it sounds like, you know, this is totally fixed and it's never going to change. And we don't like that concept in science. Ideally, the idea in science is that this is the best model we have now. If a better model comes along, we will abandon the old one and take on the new one. Now, do scientists always follow that? No, we're going to learn some stuff later where we'll learn about some scientists that their own experiments prove that they were wrong and they just simply refuse to believe their own experiments because it went against them. So we don't always have this idea, we don't always live through it, but that's the idea that we do have in science. So to show proper attitude, we're not going to call them Newton's laws, we're going to call them Newton's extremely well-supported hypotheses. So that gets a little bit long, so if you just take the first letter, EWSH, it's an EWSH. So Newton's EWSHs are what we'll call them. So no one has improved on them in a few centuries other than minor tinkering. They are indeed extremely well supported. Newton holds up really well unless you are about the size of an atom or smaller, or unless you're going pretty close to the speed of light. So if you're driving down the street going 3/4 of the speed of light and your friend is going 98% of the speed of light the opposite way, you don't pass each other at the speed you expect to pass each other at. But I know you guys drive fast, but it's not that fast, so you're never going to get in that circumstance. So other than strange things like that, Newton is extremely well supported. So there are 3 EWSHs that we are going to learn, and his first EWSH says, an object in motion tends to stay in its present state of motion in a straight line unless acted upon by an unbalanced force. Isn't that beautiful? It's such a nice EWSH. Putting that in normal terms, we like to say objects like to keep doing what they've been doing. How many of you read the notes I gave you yesterday? What did inertia mean?
Laziness.
Laziness. Yes, we all love inertia. I can't get off the couch. Too much inertia. So, inertia was a concept that was known before him. But he basically says, yeah, an object in motion wants to stay in its present state of motion. It's saying the idea of inertia. We want to keep doing what we've been doing. Now, a word from our sponsor. I just used the phrase, i.e. There are 3 Latin phrases that every educated person should know, and I am determined to see you educated. So you can squeeze these in somewhere along the side, but everybody should know these things. You should know what i.e. stands for. A lot of people think i.e. stands for in example. That would be wrong because it's not in English, it's in Latin. I.e. stands for id est. Id est means that is. That's a direct translation of the Latin. The other Latin phrase you should know is e.g. When you see e.g., that stands for exemplary gratia. Now, those of you who speak Spanish, what does this word look like? It looks like, change the last letter to an S. Free. And this looks like, what word? Example. It's a free example. So e.g. is a free example. And so what happens a lot of times when people don't really know what they're talking about, they use i.e. when they want to give an example. And really you should use e.g. because this is giving a free example. This is saying that is. Our third word, of course, is etc. And etc. stands for etc. And a lot of people don't realize that etc. is actually 2 words because you never see etc. written out. And etc. means and the rest. And most people use that one correctly. So the way we use this one is we use this one anytime we want to rephrase a definition. We use this one when we're actually giving an example. And of course, most people use etc. pretty well. So this one when I'm rephrasing. So now back to our regularly scheduling programming. Here we are, and I used i.e. Here was a textbook definition, and I rephrased it. I'm not giving an example yet. I will give examples in a minute, but here we're giving that. So I'm rephrasing i.e. Now, there's a couple of conditions to note. Notice that we have the word unless. Unless is a nice conditional word. So when you look at a phrase that has a condition in it, then you say, hey, if this is happening, then this happens. And so what we're saying is, unless it's acted upon by a unbalanced force. So he's saying this will work unless this happens. So this must work when my forces are, instead of unbalanced, the forces have to be balanced. And so balanced, of course, means equal but opposite. So if somebody's pulling me 100 this way and somebody's pulling me 100 this way, I'm going to be balanced. That would be what balanced forces are, or if they're absent. So if my forces are balanced, I will travel how?
In the constant motion.
I'm going to go in my present state of motion, and I'm going to go in a straight line. So what that says is I'm going to travel at a constant speed in a straight line. So when my forces are balanced, I will travel at a constant speed in a straight line. It's so strange. It's been erasing strange lately. Here we have our example. So here I would use what? EG. Very good. How many of you have been in a car before? Good. If you're in a car and you're sitting there in your car and the light is red, you're just sitting there. And then the light turns green and your mother's got a lead foot, so she floors it. What happens to your head? Your head does not go back.
It goes forward and then back. Your head stays.
What happens is everybody's like, Paulson, you're high. I feel my head go back. I know it goes back. Yes, what happens is your head, before your mom pushes on the accelerator, was not moving, so your head wants to stay not moving. Now, the head is the part of your body that's least attached to the car, right? The rest of you, the seat is holding on to nicely. And so when your mom floors it, then the seat goes that way and your body goes that way, but your head says, no, I want to stay back there. And so that's why you feel like your head is snapping backwards, but it's not really. When I slam on the brakes, what happens to my head? It flies forward. Does it really fly forward? Yes. See, you guys are too busy thinking just, no, there was no last time, so how do you know this time? What were you doing before you slammed on your brakes?
Moving.
I was going forward, so your head wants to keep going forward. So when you stop, your head says, no, I want to keep going. Now, why doesn't your body keep going?
Because it's also the car.
Because you are wearing your inertial restraint. So inertial restraint is a good word for that seatbelt. And of course, inertial restraint is much more fun to say. You get in your car tomorrow with your mom and you say, are you wearing your inertial restraint? She'll say, that's none of your business. Because I have no idea what you're talking about. Okay. There are places up north where ice is so plentiful that they just throw it out on the road. It's crazy. That happens here about once every 10 years. But in other places, there is where ice covers the road all the time. And when you find ice is covering the road, you will find that we have almost no forces acting on us at all. And so if we have no forces acting on us, then the only thing that does work is Newton's first EWSH, which means I'm only going to be able to travel at a constant speed in a straight line. Okay, so there was one time, 24 years ago. You guys remember that? 24 years ago, I took my oldest daughter up to the Great White North to introduce her to relatives, and they agreed that she was an adorable child. And we were coming back home, and it was just after Christmas. It was somewhere around New Year's. And we're driving south, and we're going through, like, Oklahoma City. My wife and I were taking turns driving, and my wife was driving at the moment. And as we were going through Oklahoma City, it was raining and the sun was going down and the rain was turning into sleet and it was hitting on the roads, and then the roads, after the sun went down, all that nice water on the road decided it wanted to turn into ice. And so she's driving along on this ice and she says, what should I do? And I said, what you want to do is just keep doing what you've been doing, what your car likes to obey. So we're driving along, going like 40 miles an hour down the interstate on this ice, and she's driving all nervously, and then all of a sudden our car starts to turn a little bit. So she's an experienced driver, and so she starts to steer out of the turn, but that makes her turn more the other way. And then she adjusts, and we're steering more this way, and then we're steering more this way, and every time she does the adjustment, it gets worse. But before long, we started spinning. And she was like, what do I do? And I said, take your foot off the pedals and take your hand off the steering wheels and relax. Well, she did the first two. Why was she panicking and I was calm?
Because you the first law of motion.
Because she had never taken physics. And I'm pretty well equipped with knowing what's going to happen. So I knew, here we are on this icy road, and what does my car want to keep doing? It wants to keep going in a straight line. I knew the road ahead of us was nice and straight, so the fact that we were doing this shouldn't matter. I knew my car was just going to go this way, and as long as we didn't run out of ice, we were going to be fine. So you do have air resistance pushing back. We did slow down, but it was probably 10 or 12 nice, slow around before we stopped, and we were facing that way, and she leaped out of the car and said, you drive, and I got to drive from there. But in that circumstance, I wasn't panicking because I knew Newton actually knows what he's talking about. Now, in the trunk of your car, you have this thing called a jack. What's a jack good for? Picking up your car so you can change your tire. Now, what is a jack made out of? It's made out of metal. It's a big, huge, heavy chunk of metal that you have sitting in your trunk. Has anybody ever had to get their jack out? Does it have its own special spot? Yes. Yeah. In mine, you have to take the spare tire off, and then underneath the tire, the jack is there, and the jack is like tied down also. It wasn't that way when I was your age. When I was your age, both the spare tire and the jack just kind of got tossed in the trunk, and they just kind of bounced around, and you shoved them over to the side and stuffed your groceries in, and that's just the way it was. But car manufacturers found a very interesting thing was happening. If somebody dies in a wreck, they never buy a new car. And they figured this out. And so they started saying, hey, what we want to do is keep people alive in a wreck, and if you keep you alive in a wreck, then you're in the mood for a new car because your old one just got totaled. And so, okay, so what happened is they were noticing that people were alive in the wreck until something else happened. So you're driving down the road, going 40 miles an hour, and suddenly this tree jumps out in front of you. Bam, you hit the car. You're perfectly fine because you're wearing your inertial restraint. And so you slow down when the car slows down. That's great. But the jack is in your trunk, and the jack was going 40 miles an hour, and the jack wants to keep going 40 miles an hour, and it hits the back seat. Well, that slowed it all the way down to 35 miles an hour. So now you have this large chunk of metal going 35 miles an hour that's flying straight toward the back of your head, or your torso, or something, and guess what's happening? People would have lived through the thing, but the jack was killing them. And so then that's when the engineers were saying, hey, maybe we need an inertial restraint for the jack. And so that's when they started building in these special spots where your jack fits in there and locks into place, and then your tire fits on and your tire locks down, and these things don't come out and kill you anymore. So that was a very good thing. So if you change your tire, what happens is we have a tendency to say, oh, I'm hot and I'm dirty, and I'm just going to throw this stuff in the trunk, and then later I'll put it away. And when does later happen? Typically not. So if you notice your jack in your trunk, take that extra 5 minutes sometime and actually put it away properly, and that way I don't have to go to your funeral. So that's a good thing. Has anybody ever been somewhere where you have a nice soda and you've got this annoying chunk of ice that's right in your glass, and you spin your glass, and what happens? The ice just stays right there, right? Why does the ice stay there?
Because there's no need.
If it's not moving, it wants to stay not moving. So what you have to do is outsmart your ice. What you want to do is you want to walk to this side. And now the ice is over on the other side. This is a cool experiment to do tomorrow. Get up in the morning and have your crunch berries for breakfast. And leave one of them on top of your milk. And then I want you to pick your bowl up, and I want you to walk around it. Okay, don't do this, you'll make a big mess, okay? But grab the dish and walk around it and stare at the crunch berry. You'll be very impressed, and your mother will be like, what are you doing? Like, come here, you gotta see this. And you have her try it. And she'll be like, what is that? And you're gonna say, inertia, Mom, duh. And she'll say, you're so smart. Okay, on the dashboard, back in the day, we used to have these things called CDs. Nobody has those anymore because everything's stored in your phone. But we used to have these things called CDs, and you put them up on your dashboard all the time. And that worked out great until you turned a corner. What happens when you turn a corner real sharply? Have you ever had something up on your dashboard? And what happens to it? It goes sliding across the thing. If your window happens to be open, what happens is you make a sharp left turn, and all of a sudden it's right out your right window. And so what you used to see, back in the day, you used to see CDs, and before that you saw cassette tapes. They were even better because cars would run over them, and then you had this little tail of streamer running all the way down the street. But you only saw this happen at an intersection. You never saw it happen in a straight stretch of road, but there were always a bunch of dead cassettes in the middle of the intersection. And that's because if I'm driving down the road this way, my body wants to keep going this way, but then when my car turns this way, it still wants to go, which is why you slam into the person next to you when you're taking that sharp corner, because your body's trying to keep going straight. Your car had that annoying, I'm changing directions, and your body says no. But if you're like a cassette sitting on the dash, it's just going to keep going that way. So that's going to continue to happen. On the interstate, how do you drive? Fast. How else do you drive? straight and at a
Constant speed.
hey, if you're driving at a constant speed in a straight line, Newton says your forces are balanced. So shouldn't I just be able to get up to 75 and shut my car off?
No, because the acceleration of the car will the velocity.
Shouldn't I just be able to cruise at a constant speed in a straight line forever?
No, because there's friction that's slowing you down.
There is friction, and it's predominantly on the interstate. Your predominant friction is actually air resistance. If you've ever stuck your head out of the car when you're going 5 miles an hour, it's kind of a nice feeling through your hair. If you're going at 75, it's not such a pleasant experience. Yeah, especially when the bugs get you. A little tiny gnat at 75 in the back of your throat, it feels great. So when your car is on the interstate, what Newton says is, yes, you still have balanced forces. But what happens is the air is pushing this way, so my car still has to push that way to fight air resistance. But really the only reason my car needs to keep pushing is to fight air resistance. So what happens is, when I was a little kid, they used to have these things on the road that looked like this. Has anybody ever seen one of these before?
Yes.
You live in Laredo, especially those of you who live on Mines Road with me. We see these a lot. Now, this is the way they looked when I was a kid. Because when I was a kid, gas was 25 cents a gallon.
So I haven't checked now.
And then when I was in high school, it was all the way up to $1. Which actually at that time was more than what we were paying here, relatively speaking. But that was when one of the presidents decided to do something about gas prices, and he made everything worse. So anytime a politician says we're going to do something, start being scared. This is the way trucks looked when I was a kid. What got added?
Oh, the advertisement? No.
What got added was a little piece of plastic that goes like this. If you've ever been behind one of these when this was not attached, then you look in the back of this, you see that it's just empty. And you're like, why do they have this thing? Well, if they don't have that thing, then as this is going this way, the air appears to be going that way. And so the air is smacking into here, and the air is smacking into there, and it's got all these nice flat surfaces that it's just smacking into. And that slows it down. It's like having a big umbrella behind you. But when you put it on this little piece of plastic, now suddenly it's going over the top, and it's a little more aerodynamic, which means if the air isn't pushing back as hard, I don't have to push forward as hard. Now, this little piece of plastic means that this truck gets about 3 miles per gallon better. And you're saying 3 miles per gallon, that's no big deal, until you understand what the mileage of one of these is. Now, in your car, that probably wouldn't be that big of a deal, because if you're getting 28 and suddenly you're getting 31, well, sure, that's better, but that's not that much better. One of these without this gets about 8. One of these with this gets about 11. Is that a substantial difference? Yeah, when you look at percentage-wise, that's like a 40% increase in your fuel. That means I pay 40% less for my fuel costs. If I was a driver, I would really like one of those. And so now they're starting to flirt with other stuff, like you're starting to see things in the back that are funky things that are in the back that look weird, and it's like, what is this doing? And that's because behind the truck, instead of getting this nice ideal, if you have your truck at this end, we get what's called turbulent flow. And what you want to get is flow that comes out in a nice line, and those little things at the end help to get it to go in a line rather than the turbulent stuff, and that gives you, again, better mileage. And when you're getting that kind of mileage, you want every increase you can get. So, interesting stuff. I always wondered, what kind of mileage do these trucks get? And you know how I found out? I talk to truck drivers when I'm getting gas. What kind of mileage does that thing get? About 8. Okay. Now it's interesting. You actually talk to people. Pigs in space. Anybody was a Muppet Show fan when you were looking? Remember pigs? When you are in space, is there any air? Is Is there any air resistance? Guess what operates real well in space? Newton's first EWSH. Once I'm out in space and I'm away from the air, I can shut off my engine. And just like I wish I could do here, I should just be able to get up to 75, shut it off, and go all the way to Canada for free. That would be great, except we kind of need air here. But out in space, there is no air, so there's no air resistance. So once I am going, all I have to do is shut everything off. And I keep going at a
Constant speed.
And it works like that. So when we went to the moon, we just traveled at a constant speed in a straight line all the way to the moon. We pushed until we got up and out, and then pointed toward where the moon would be in 3 days and shut the thing off. Let's nap for a couple days and wake up when we get close and readjust from there. So if they had to keep pushing the whole time they were in space, we couldn't have lifted that much fuel up. It never would have worked. So it's kind of nice. So if you're out in space and I give you a nice shove and we're out in the middle of nowhere, guess how long you're going to travel at a constant speed in a straight line? Forever. Forever. How many of you are Sandlot fans? That's it?
I didn't even
I don't know what it is.
You never saw the Sandlot?
Oh, it's not bad.
I didn't hear you the first time, so I was
When
like,
I said forever, that should have. Never mind. Okay. So Newton's first EWSH said we're going to travel at a constant speed in a straight line unless our forces are unbalanced. So what happens if our forces are unbalanced? Well, Newton handles that with his second EWSH. He says if we have an unbalanced force, we're going to get an acceleration that's directly proportional and in the same direction to the force, but it's inversely proportional to the mass. That tells me that the acceleration will be directly proportional to the force, inversely proportional to the mass. We usually bring the m up, and we get F equals ma, which is the most important formula in all of physics. Isn't that pretty? So we have some new terms here. You may not have ever seen these before. Force, mass, and acceleration. What are these talking about, man? Well, we know acceleration, of course. Anytime we see meters per second squared, we know that's going to be an acceleration. That's going to work out fine. On the other hand, if we see mass, mass is how much stuff is there. How much stuff you have is how much inertia you have. If you have more stuff, you have more inertia. How many of you have been behind an 18-wheeler at a red light before? What kind of acceleration do they get? Yeah, really, really, really tiny accelerations. Because, again, you got that much mass, you got that much inertia, that much laziness. Get it going, man. On the other hand, if you're on a motorcycle, what kind of acceleration do they have?
Really quick.
Yeah, really fast acceleration. So we like those. The unit of mass should be a gram, but grams are so tiny that we use kilograms as our standard mass. So a kilogram, that's about 2.2 pounds. So that's our unit of mass. Force is new, and forces, of course, you learned yesterday if you read those things, are anything that pushes or pulls. Anything that pushes or pulls we call a force. And the unit for force comes from the unit, it comes from this formula we just had. Mass is in what?
kilograms.
Kilograms, and acceleration is in meters per second squared. So if I multiply a kilogram times a meter per second squared, I'm going to get a kilogram meter per second squared. Tricky, right? But that gets a little tedious. So a kilogram meter per second squared is also known as a capital N, which stands for, yay, it stands for Newton. So we named Newtons after Newton because it only fits. So let's try a problem here. Jackie shoves an 8.67 kilogram box across the floor, accelerating at 2.93 meters per second over 14 meters displacement. How hard was she pushing? What do we know?
Kilograms.
When we see kilograms, we're now thinking, We see meters per second, we think. Velocity is its initial or final. If we go from something to something, the to is always the final, the from is always initial. There's not a from here, but there is a to. So that means, that means it has to be final. And then we have 14 and we see meters, it has to be displacement. So we're looking for how hard she was pushing, and when we see pushes or pulls, we think F. So my V initial here has to be 0 because boxes usually just sit there until somebody comes and shoves them. So we're looking for force. And again, the only force formula we know so far is F equals ma. So I know my I don't know my A. Do I cry? No, because last week we learned how to figure out A. So now we have to say, hey, how do I get A from VF and D and VI?
Oh, what's it again? VF minus VI over T.
Do we see T anywhere there?
So you switch
No, which formula didn't have T in it?
VF squared minus
Yeah, that one. So if we have this one and we rearrange it for A, it's going to look like that. And we have all those numbers. And then once we get to A, we want to multiply it by the mass. So I'll let you try that. Plug in those numbers you got. They don't go.
$3,100.
Did you remember you gave the decimal?
Oh, yeah.
So ideally you got 0.306603571, and then that was the A, but we need to multiply the A times the M. So we take the M times what's already in our calculator, and then we round. That part's really easy. So this tells you that last unit doesn't disappear. If you didn't know how to do the A part, you're going to be in trouble from what we're going to continue forward. I do want to go backwards just a minute to Newton's second English here. I didn't spend as much time as I should have on the definition here. So what we're saying here is our unbalanced force is going to produce an acceleration. Now, it's not just that F equals ma, but it's also, we see that it is directly proportional and in the same direction. So what does this tell you? If I shove on you with a small force, you get a small acceleration. If I shove on you with a big force, you get a big acceleration. That makes sense, right? If I give you a little shove, you get a little acceleration. The other part is the direction. And I know this sounds like it makes perfect common sense, but people still get confused on it. If I shove you that way, your head is going to go the way I shove you. It's not going to go flying off to the side. And you're like, well, duh. Well, what happens if you're running toward me and I shove against you?
You're gonna stop and keep going forward.
I'm going to stop you. What kind of acceleration was that?
The opposite. Negative thing?
If you're coming toward me and I push against you and I slow you down, that's a negative acceleration because I gave you a negative force. I was going against your motion, so that's a negative force, so it caused a negative acceleration. Does this make sense? You'll need to understand that for what we talk about on the third. The other part is here, then the force is going to be inverse to the mass. So if it's inversely proportional to mass, that means if I shove on a little thing, I get a inverse means it's going to be the opposite. So if I have a little mass, I'm going to have a big acceleration. If I have a big mass, I have a little acceleration. So if I take Bob, Bob is about the same size as a soccer ball, right? So if I kick Bob, no. Why would I not want to kick Bob? Because a mass this big will have what kind of acceleration? Very small. So instead of my foot continuing through on its motion, my foot is going to stop real fast, and that's going to break something in my foot, and I would be sad. So Bob does not like to accelerate like a soccer ball. A soccer ball is filled with air, so the mass is very small. So when I smack it, yeah, I can get a nice big acceleration out of it. My foot doesn't slow down much at all. But if I try and accelerate Bob, it would be no. Just like if you're behind the 18-wheeler. You're like, please accelerate faster. I want to get there before I die of old age. But they can't. They have to go slowly. So once they get fast, guess what happens when they try and slow down? Hey, it's hard for them to slow down too, so don't jump in front of them and then slow down because they will just run right over you, and it's not like they wanted to do that. They can't stop. So going back to where we used to was. This will be faster if I just jump.
What was the final answer for the problem with it?
The final answer was 2.66. So we're jumping to Newton's third EWSH. And Newton's third EWSH is the one that most people have heard of, but most people misunderstand the most. Every action force has an equal but opposite reaction force. How many people have heard this before? Yes. Now, if you've heard this, you probably heard this with less words. What word did they not have up there? Force. All the time you hear every action has an equal but opposite reaction. Well, that's great, but then you get confused. What's an action? What's a reaction? It's like you think, oh, I flirted with Cuddy and she slapped me. That was the action-reaction. That's not what we're talking about. Action-reaction is always force. Every action force has an equal but opposite reaction force, which means forces always come in pairs. But if forces come in pairs and they're always equal but opposite, does that mean nothing can ever accelerate? No. That we're talking about two forces acting on the same object. What's happening here are the forces are paired, but they're acting on different objects. So if I'm kicking Bob, what it says is Bob kicks me back. Does my foot notice that? Yes. Definitely. It's going to notice that. He's going to hit me as hard as I hit him. But he's going to be in the opposite direction. I'm going to try and speed him up. He's going to try and slow down my foot. It's opposite direction. But notice how we have the same size force, but my force is acting on him. His force is acting on me. It's not both forces are acting on one object. The two forces are acting on different ones. And of course, they're pushing in opposite. How many of you have been swimming before? No matter what stroke you do, even if it's the dog paddle, you're grabbing water and shoving it. But what direction are you shoving water?
Opposite.
If you've ever actually thought about it, you grab water and you shove backwards. Or I reach out, grab it, and pull it backwards. I'm doing a backstroke. I reach back and pull it. I'm always shoving the water the opposite way I want to go. Well, who's going to win the race? The water wins. No, but if I'm competing, like, I will race against my children, and I usually win. Why? I'm bigger. And I realize if I want to have the water shove me harder, I need to shove the water harder. And some kids just don't get that. And so they're in there going, and you gotta go, So, yeah, I mean, you see the real swimmers, and they're in there grabbing as much water as they can and shoving it back really hard, and for some reason that works. Have you ever been in a boat where you have a paddle?
Yes.
What direction are you shoving the water? You always grab the water and shove it backwards, and that shoves you forward. Okay, so if, say I'm going to hit Anthony in the face. Okay, so if I come up to Anthony and I smash him in the face, his head is going to accelerate that way, but what happens to my hand?
Stop.
It stops. So if my hand stopped, that had a what kind of acceleration? A negative acceleration. Well, that had to come from somewhere. Where did it come from? His face. So his face hits my hand just as hard as my hand hits his face. So can I sue him for beating up my hand with his face? No, the court looks at intent, and nobody says, oh. It's not going to happen. So, but have you guys ever watched a little kid play t-ball?
Yes.
When a little kid is playing t-ball, they miss sometimes. The ball's right there on a tee, and they miss. What happens when they miss? They miss, and and they spin all the way around. Why do they spin all the way around? Nothing slowed down the bat. So it had plenty of inertia, and it wanted to keep doing what it's been doing, so it spun around. When they make contact with the ball goes flying, but the kid does not spin because the bat slowed down. Why did the bat slow down? Because the ball hit the bat just as hard as the bat hit the ball. Now, is the effect on both of them the same? No. I mean, when a fly smacks into an 18-wheeler going 70, I assure you the fly notices that more than the 18-wheeler does. But the force is the same. So it's not the acceleration that's the same, it's the force that's the same. So the ball accelerated more than the bat did because the bat's bigger and attached to the kid. And so their combined mass, it didn't slow down as much as the ball increased. But it is the same size force. Jumping. When you jump, what direction are you pushing?
Down.
You're not pushing up. If you don't believe me, you can put your face here and I'll jump on it and you'll see what direction I'm pushing. When I jump, I am pushing down. Now, what direction do I go? Up. And so people get confused. Oh, I must be pushing up. Well, you're not pushing on yourself. What are you pushing on? You're pushing on the floor. So what are you trying to accelerate? When you jump, you're actually trying to accelerate the floor downward. Do you do a good job with that? No. But then the floor pushes you what direction? Upward. So the only reason I go up in the air is because the floor is pushing up on me. Weird, right? You're like, I didn't know the floor was working out so much. No, it's not that kind of push, but it's that kind of force. So the floor pushes me up. Now, Michael Jordan is one day older than I am. At his best, he had a 48-inch vertical leap. At my best, I had about a 28 vertical leap. How come the earth likes him better than it likes me?
More strength.
Solid.
He has more strength and strength.
He applied more force. If you look at my thighs and you look at Mike's thighs, you see that Mike has the ability to push down harder than I do, which helps with the ground pushing up just as hard as you pushing down. So, I'm trying to push what again? I'm trying to push the ground. So if I'm trying to push the ground down, shouldn't I be able to move the earth? What? Only Chuck Norris can do that. No, actually, I actually do move the earth every time I jump.
Very little.
Yes, but again, the force on me, since my mass is small, you notice a pretty good size acceleration, but the Earth's mass is quite huge, so the acceleration would be really tiny. But every time I jump up, the Earth actually accelerates downward slightly.
So if everyone in the whole entire world were to jump in.
That's the question.
Oh my god.
What if everyone on Earth jumped all at the same time? So is the Earth going to go careening off its path and plunge into the sun and we're all going to die?
No, it can be opposite forces.
Okay, now, yes, we always get the people that say, okay, no, we're over here and people in China are over here and we're jumping opposite ways and so it just like cancels out. No, that obviously isn't going to work. So we're going to invite everybody in the world over to my backyard for a jumping party.
It's a big backyard.
Okay, it's a very big backyard. Now, this is the way Newton's third looks in formula form. You may want to write that down or circle it or something. Every force has an equal but opposite force. So we also learned Newton's second here. We said F equals ma. So every ma has an equal but opposite ma. Now, so this is basically the Earth is on one side and the whole mass of humanity is on the other side. The mass of all the people on the Earth is about 7 billion people. And we're going to pretend that they have an average mass of 68 kilograms, which is about 135 pounds. Now you're saying, but Paulson, you're heavier, 135 pounds. Yes, but 3/4 of the world's population is under the age of 12, and there's not that many people that are 6 years old and weigh 135 pounds. So this is probably an exaggeration. Anyway, that would give our total mass of humanity around this number. That's a pretty good sized number. Now, let's pretend our average acceleration is 81 meters per second. We've all got hops. We'll pretend Grandma's not, she's still got it. It could happen, sure. All we need to know now is the mass of the Earth. And of course, everybody knows the mass of the Earth is about 5.98 times 10 to the 24th kilograms, right? You all have that memorized. So what we're doing is we're taking the ma equals negative ma and we're moving this underneath. And so we're going to look like that. And if we plug in all of our numbers, that gives us that, which if we put it in normal number form, it's going to look like that. So if everybody in the world was in my backyard and they all jumped at once and then you stood behind on the ground just to feel it, that's how much of an acceleration you would feel. Would you notice that? No. What if we got all the elephants to jump? Elephants can't jump, so that wouldn't work too well.
Mr. Paulson,
Yes.
what about when everybody hits the ground?
Well, that's the whole deal. We all jump up, and the Earth moves slightly down, and then we fall toward each other. So the Earth is falling back up as we're falling back down, and it's going to cancel out again. Yeah, well, you would notice it if you were on a little tiny asteroid. Now, if we all went out to a little tiny asteroid and jumped, then we would notice it happening. If we're out in the space shuttle and you jump in the space shuttle, everybody else in the space shuttle actually feels it move. Now, does it move a lot? No, the space shuttle is pretty big compared to you, and so if it's 10,000 times bigger than you are, then you're going to notice you 10,000 times more than the space shuttle, but it is something that you can actually feel. Interesting, right?
Yeah.
Yeah. Okay, here we have an exciting video. This is a scrawny little girl that I had in class about 10 years ago, and this was the first time she ever fired a 12 gauge. Has anybody shot a gun before? This is Texas. You guys should all be raising your hands. Okay. If you've ever shot a gun before, you know Newton's third EWSH. Because when the gun shoots the bullet shoots the gun. Now, which one has a bigger effect? The little tiny bullet has a big acceleration, and the larger gun has a small acceleration, relatively speaking, but still. Yeah, you'll notice that she went back pretty well there. I have a friend who served like 4 tours of duty over in Afghanistan and Iraq and Iran and not Iran and Yemen and all these different places over there. And he would always send me pictures of the new gun that he's using now. And he would always send me pictures. And the reason he sent me pictures was he was 12 years old and I took him out shooting. And so we were shooting with a .22, which is a little tiny bullet, and it doesn't have much of a kick because it's a much smaller explosion. And he was getting pretty good with those and having fun with those. And so then I said, you want to shoot my big rifle? So then we got out a 30-06. 30-06 has a cartridge that's about this size compared to the .22 is about this size. It's also much fatter. So there's a much bigger boom. So it was fun. I had him lean into it. You know, he's all of 115 pounds at that point. And he's leaning way into the shot, and he shoots, and he goes flying backwards, and I catch him. His eyes are huge, and he looks at me and says, "Can we do it again?" So he says I was the one to blame for all his gun crazy stuff. So every time he got a bigger and bigger gun over there, he would send me a picture. Look what you did to me. That's kind of funny. Okay, to sum up, we're going to do this another day, but your car mileage. I used to have a car, and then I had a bunch of children, and my wife said, "I want a bigger car." I can't imagine why. She goes, "I don't care what kind of car it is, I want 4 doors." Because it's a pain getting little kids in and out of the back seat when you only have 2 doors. And so we got a larger car, but the larger car was more aerodynamic than the old car was because things had changed there. So what happened to my in-town mileage?
Lower or higher enough.
In town, what are you doing?
You stop.
Starting and stopping. We also call those accelerations, right? So you're constantly accelerating. So which EWSH counts most for in-town driving?
Second.
Second, where it has the F equals ma. So if my car got bigger mass, then I needed a bigger force to cause the same acceleration, which means my gas mileage got worse. It's not as good. I went from like 25 down to 21. What happened to my interstate mileage? On my interstate mileage, we're only concerned with Newton's first law. Yes.
Do you have Oscar Lina?
Yes.
To the front office, Mr. Avila, a couple of minutes.
Okay.
Thank you.
So our interstate mileage, Newton's first EWSH, is concerned only with the balanced forces. So if I have less air pushing backwards because I'm more aerodynamic, I don't have to push it hard forward to get it to go to the front. And so my gas mileage went from like 35 to 43 or something like that. That was the coolest car we could drive everywhere for like nothing. With 43 miles to the gallon. Football players. What's the purpose of alignment? To block. So do you want them to accelerate or do you want them to not accelerate? You want them to be very hard to shove around. So what size do we have for linemen? Very big. So we have these huge masses involved there. When you look on the football field, the largest guys out there are the linemen. What's the purpose of a running back? They want to be able to accelerate, change direction, speed up, slow down, move, wiggle, get hard to tackle. Who are the smallest people out on the football field? Usually the running back. So it's almost like it makes sense or something. There's always some physics behind it. So for homework, of course, you want to do? You want to do homework. Okay, so